Now that we've solved our problem and found the voltage across the inductor, let's take this phasor representation of the solution and turn it back into the time domain. So if we can remember from our Euler's identity that the amplitude just comes down, we have a cosine function. For the frequency, if you recall, we get the frequency from this source right here, which was 4 times 10 to the 4 t, and then minus our phase angle of 83.1 degrees. So again, our amplitude is from here. Our frequency comes from the frequency of the source, and our phase from the exponent just comes down. Now, to get a better sense of what this answer means and to understand how the resistor and the inductor affect the circuit, let's look back at what the original driving signal was. So our original source signal was 15 cosine 4 times 10 to the 4 t minus 120 degrees. And so to get an understanding of what happens in a AC circuit, let's compare a couple components. First things first, the amplitude of the signal has changed. So when we measure it across the inductor, it only has a magnitude of 12 volts rather than the 15 volts that came from the source. This drop is due to our resistor, as always, dropping some voltage across it. So it has dropped some amount of voltage across it by the time it gets to the inductor. The second change we should notice is that the phase is different. So our original phase was 120 degrees, and now our phase is negative 120 degrees, and now our phase is minus 83 degrees. What this means, though, is that the inductor's wave is actually in front of the source wave, as its phase is more positive than the reference. So if this was actually sort of a zero phase angle, this would have a positive phase. This would have a positive phase, as it would be in front of the other source. The one thing to notice, though, is that the frequency of the signal is not affected. So in our circuits here, the amplitude gets affected by the resistor. So our amplitude is affected by the resistor, and our phase is affected by the inductor. And so if we were to draw this graphically, so if we sort of look here over time, if the black wave is our reference wave of the source, so Vs of t, then our red wave, which would be across the inductor, would be a little bit less, but then also a little bit in front in terms of time of this source. So VL right here would actually be in time in front of Vs. And because of the resistor, it'll actually be a little bit lower in amplitude. So as we go forward, we'll use these combined properties of both the resistors, the inductors, and the capacitors when we make filters. And what we will actually do there is just completely destroy signals of a certain frequency by moving them completely out of phase and then reducing their amplitude of the signal.